Welcome to the June 2025 GoldSim webinar on simulating flow control. My name is Jason Lillywhite. I work for GoldSim Technology Group, and I'm here to share thoughts and ideas, but mostly introduce to you a new GoldSim element, but my thoughts and ideas on simulating flow control in dynamic simulation. And this topic is very interesting to me because when I first started doing building dynamic simulation models, I was just coming out of the world of doing a lot of hydraulic modeling for pipe and canal systems, and getting into more of the dynamic aspects of how they change through time. And I moved in toward a tool like GoldSim when I was a consultant, because we were building models that were what would be the word they're interdisciplinary type of models that, for example, may have included some of hydrology and hydraulics, but also economics, policy, water rights, environmental law, that were also incorporated into these models and required a more general tool. So spreadsheets are always one option, but they're hard to read. Once you build them, they're hard to maintain, and they're hard to scale, and for a lot of reasons. They do have there are a lot of good things, and there are also a lot of limitations, just like any tool. But with GoldSim, you're able to get a little closer to simulating both human actions and also automations, and natural dynamics that occur in the real world. And so modeling flow control is a key component, actually, to a lot of types of models, particularly with water balance models. So what is flow control? Flow control is a way of regulating the movement of water, essentially. And it doesn't have to be water. It could be energy or any kind of material that you're moving through a system where you've got flows that are then affecting the state of some system. And I'm going to be focusing in this webinar on water flows, but just imagine it could be used for other types of processes as well. The point of flow control is to maintain stability, or maintain some sort of target outcome in your system. And in a water system, it would be something like maintaining a water level. And the point of flow control is that it responds dynamically using feedback as the system changes. And it's commonly used, actually, in the real world, both in actually controlling the system, but also in simulating the control. So we're going to be talking about the similar concepts, actually, that are the same, both in simulation and in the real world. So here's a real world application. It's actually a simple model, but I was going to show a larger model, but it's harder to visualize flows in just a very short demonstration of it. But without going actually into the model right now, I just want to talk about it. So you can see the image over here. There's a stream represented by these three boxes. They're called containers in GoldSim: upstream, diversion, downstream. So that's really our kind of on the side. That's kind of outside of what we're trying to model. It's the source of our water. So we need to include it, and perhaps we're trying to protect its resource, right? So there are decisions that have to be made to pull water from this river. And then once it's in our system, we now need to manage it. And we manage it using flow control. So there are all these lines going in different directions. Some of them are not controlled, and some of them are controlled. And it's really important at the beginning, when you're designing your model, to think of your system this way. What do I have control over? Maybe not what do people have control over necessarily, but something's controlling. So let's talk about this cycle. In a more schematic representation here, we have the controller represented in this big box, and there's these three components within it: the error, And the error, like I mentioned, is the difference between the target and the process state that you're monitoring. And then that error, and these need to be compatible, target and process, okay? So if we're monitoring water level, then the target must be water level. If we're monitoring volume, target must be volume. Okay, so units are compatible. We feed that information into the controller. Some properties are used, such as tuning factors, that allow you to adjust the stability in its reaction to the error. And then it provides an output that then controls some sort of flow. So we have these things called, we have state variable. That's the output of coming from our process called state variable. That's the thing you want to control. And we have the controller, we have the target, and we have this feedback loop. So those are the parts that are interacting with the controller that we need to keep in mind. Okay, so there's two directions of flow that we need to also consider. If you have an outflow type of control, of flow control, then as your process variable is increasing, then simultaneously your controller output will also increase. If you have an inflow, then as your process variable is increasing, then your controller output will be reducing. Okay, so let's talk about the controller element in GoldSim itself. In GoldSim, the controller element is in the functions category, so you pick that, go down to controller, and then add it. Here's an image showing the controller element in GoldSim. And you can see that a process variable is labeled here. That's just coming from probably a reservoir. And then we have a controlled request, which is going to drive the outflow. So probably going into the outflows request of a pool element, for example, would be a common way to set this up. Okay, so it's new in GoldSim 15, our latest release. And it's essentially replacing, I mean, we could build what the controller does with other GoldSim elements that have already existed. We have been doing it for years. But this kind of just standardizes things because I've looked at a lot of models from our users when they have questions, and before I delete them, I just kind of take a look at them. I try to just understand how some things are being done and just kind of take notes. And so when we were designing the controller, I made a specific targeted kind of a research attempt at looking at all how people are simulating flow control. And we did see that this element would replace or could easily replace most. There are some cases where you might be using a lookup table to do something like a rating curve or a response curve. And so you'd still be using that. I mean, it's just a lookup table and it's not really that complicated. The other options can get more complicated. So when you open up the controller element, you see here's the properties dialog that appears here. And notice the flow units and quantity units are separated here and both identified because some of our input is a process variable that's in quantity units and our output is a flow. So we want to include both just because you might be reporting on either one of those kind of things and just to keep things consistent. Process variable needs to be just an input from some state variable in your model. And typically this would be a reservoir, integrator, and most likely pool element. But if you had a water level as a target, you would have to convert it to a volume before putting it in here. Okay, so the next step is to define the flow direction. And in this case, we have set up, this is set up to be inflow. The default is outflow. Then you can set the flow capacity. This would be analogous to like if you were simulating a variable speed pump, it can vary its flow up to a point where it hits its capacity. That would be the capacity. And this doesn't have to be a static value. The next one is the method of control. In my case, I've got a proportional control type of controller that I'm looking at right here. And the next is the target or set point, as it might be called. And this is your desired value that you want the process variable to be. And then we have these two other terms, bias and proportional gain. And these will act more as tuning factors for you. GoldSim provides 3 types of control. These are selected here in the methods properties area of the element. The deadband controller is a type of flow control that is turning on and off with no other. It's a binary, essentially a binary output, and so you see its output looks like this. What's shown in this red line here. In this case, we're controlling outflow from a reservoir with uncontrolled inflow, and you can see the result here. Is the black line. The black line is the process variable, as it's called, the thing we're trying to control, right? And the output of the controller is the red line. And so the result is here is our target, this dark green line. And the model is trying to control that flow so that it stays within the deadband around this target. GoldSim provides 3 different positions of the target relative to the deadband. And so you can define it in these ways. It can help you in situations where your target is at a bound of a reservoir. So maybe at the bottom of the reservoir, oftentimes you have a reservoir or pond that's sole purpose is to provide empty capacity in case there's a sudden inflow. And so your target might be at the bottom where you're just trying to keep it empty all the time so that it's always ready, that kind of thing. Another type of controller it provides is the proportional control, and this is just a proportional outcome to the error, essentially. So it looks at the error, which is the difference between your target and your process variable. That's the red line and the dashed red line here. It looks at the difference between those two. And as that difference grows, then there is a proportionally growing output. The next method that we provide is the PID controller. And this stands for proportional integral derivative controller. So there are 3 components to this type of control. The proportional is there just as it is in the proportional controller. Same thing. But then we also have an integral factor, which is the amount of error that is integrated over time. And then the derivative, it looks at the change. So perhaps you want to prevent too rapid of a change in your system. Then you can do that with the D term. Okay, so now I'm going to go into some model examples and talk about their basics. So I'm bringing my first model over here. This comes with GoldSim. So when you download GoldSim 15, you can go up here to File, Open Example, and go to General Examples, and you'll see there's a whole controllers folder. There's a whole bunch of examples in here. I recommend going through those. So when we run this model, so I'll go ahead and run this, and we can get an idea of what's happening just by looking at the result here. But you see here that in this particular case, we have an inflow coming in. That's this red line. And then we have here the volume is increasing and then decreasing. And it's kind of got this sawtooth nature. And that's how you know it's a deadband. When I see this, I see deadband. We'll talk for a second here about this big spike. But before we go there, let's look at the properties so we can understand a little bit more about how this thing is set up. Okay, so we have a flow rate and we're controlling a volume. The volume is this pond here that we're controlling. That's the process variable. We are controlling an outflow. The pumping rate is this value here, which we could go look at, pumping rate. So function of pumping rate. It's just a constant. That's all it is. All right. So deadband, that's the method we're choosing. And we're going to use the target and thickness. There's another way to define a deadband, which is explicitly defining the top and the bottom boundaries of the deadband. And then our target here, and in this case, it's in the middle of the deadband, and our deadband thickness. So our target volume says 3,000. Our thickness is 50. So it's a pretty small band within the full range of volume. The initial flow state, this is what it's going to be doing at time 0. This is important for a deadband type of controller because if you start your simulation within the deadband, there's no real way to say if it's on or off at time 0. So we have to specify that. Finally, you can add additional on and off controls, such as a power outage causing the thing to stop operating, that kind of thing. And it looks like that's what's happening here. Initially, the thing is operating, and then we can click on this turn off event button, and you see that we have at E time 50, we're going to turn this thing off. And then it looks like 10 days later, we're going to turn it back on again. So that's what's happening here when we run this model, is that the thing just stops operating. And we've got this inflow up here that's above. Well, let's also add the outflow, shall we? So I'm going to add a green line that is the outflow we're calculating, or the outflow that we're controlling. Change that to green. Okay. So, so you can see here that our capacity is slightly greater than the inflow, which is beneficial to us. That means we'll always be able to control it. But then we get to this point where it just shuts off and stops operating. And so inflow just keeps coming in until it's allowed to start up again. Once it starts, then it drains it back down, gets it under control again. So that's the deadband controller. Okay, now let me go into another example. Let's talk about the interconnected ponds model that I showed you earlier. Okay, so here's the model. And now I just want to show you, if I go into pond 1, you'll see we have a controller. And so if I open this, you see this is looking at pond 2. So this is going outside of this container. It's looking at information coming to it from pond 2. The reason for that is because this pond 1, you can see it says pond 1 up here, by the way. So I like to use containers to, we could use containers, and we could also use the note pane. But anyway, so we are in pond 1 right now. I really do need to just make a quick note about that, by the way, that if you're going to build a model this way, I recommend using the note pane heavily, because when a reader comes into this model, it's really important for them to understand where they are. And yes, it's true that the address bar shows pond 1, but I like to, when I'm in a container that means a really important component of the model that I want people to know about, then I would put in large font, where we are currently. So we are in pond 1, and we are monitoring pond 2. And by the way, if we go up here to the flow network, there is no influence line from pond 2 to pond 1. And I did that on purpose because I'm filtering those lines out by using system references, where I'm putting the things that are essentially broadcast. These are like this is where I broadcast information, essentially feedback between components. And it's not water flows that I'm talking about referencing here. I am referencing information. It could be a flow rate, but it's really just, you think of it as you have a level sensor in your tank, in your water tank, and you have to communicate that information back over to some other equipment somewhere using radio signal or something. That's the thing we're simulating, that process of that information coming back over here to pond 1. So instantaneously, right, we get that information. Here's pond 2. We're going to make a decision based on that. We're going to use this flow capacity and throttle it down if necessary to get us to be stable and right at the target that we're watching for. The target that we have is this value 22. We're going to do everything we can to keep 22 cubic meters in that pond 2 over there. And we're going to use a bias here because we've got an uncontrolled inflow that's on average about 1.5. And then I'm going to use a proportional gain of 0.6. So now when we run this, go up a level and look at the ponds together, then we get a better idea of what's happening. So now we see that pond 2 was high. Pond 2 was low at the beginning, and the response was to send a lot of water, that's this green line, to it to fill it. So the green line is water we're sending to pond 2, and the blue line is its response. It's filling. It reaches nearly the target, and as it approaches the target, we throttle down the flow to feed it to get to that target. And then you see it starts dropping away from the target, but that's not under our control. Okay, so the same thing could be said about pond 3. It's a similar type of a thing where pond 1 is going up and down. You can see when pond 1 is below its target, that's when we are sending water over to pond 1. Okay, so another example that I want to show is, let's see, let's look at this one. So this model compares 4 different types of controllers, and I do that with the scenario manager. So here are my 4 different controllers. If I run all, close, then look at a chart, and I'll just go to one scenario at a time. So here's the deadband, and you can see that it's showing the sawtooth formation that I was talking about earlier. However, you should notice that there are times where it doesn't look like we're exactly touching. So that's where we need to talk about briefly unscheduled steps. So these lines that you see here, I've just drawn them. I mean, I've plotted them by capturing their values by adding half of the deadband to the target. I know the target, that's this value right here, this guy. So that's this middle line, and it stair steps, by the way. I just wanted to show what happens when it's dynamic. The deadband is depicted with these lines, and what we should see is that GoldSim will insert a time step at exactly the moment it hits that line, and this operates the same way as when you hit a upper bound and a lower bound in a reservoir. There's a time step inserted, and it happens at exactly the moment that that bound is hit by its value, by the process variable in this case. So what I want to do now is go to the simulation settings, go to the advanced, and make sure that we say include unscheduled high resolution results in time histories. Now, I was running a scenario, but what I want to see now is I want to do a regular run that is not in scenario mode, and I'm going to make sure I have the deadband option active because I want to see the deadband result in high resolution. So I cannot run a scenario. I need to do a regular run. Here we go. And now we see that the line is always being touched. And this is because if we go to table view, you'll see that we have inserted time steps. This is 27.7 days. And we have hit the top of the deadband with reservoir and top of deadband. You see the numbers are the same. Then we get here to day 30.7, and we have now hit the bottom of the deadband. So that's when time steps are being inserted in this case. Now let's do another comparison. Let's compare this option to if statement. And I'm using if statement. It's not a type of controller. It's a type of functionality that we've built. I included when I first started using GoldSim as a way to control flows. And it's got some problems with it, which we'll see here in a second. Okay, so now I'm opening up the same chart. This is how the if statement works. It is fully dependent on when the next step will occur. So if you have an unscheduled step, maybe it came from some other place in the model that will impact this. It's basically going to operate okay, but when you look at the detail, it starts to become very problematic. So let's change our time step to 1 hour just to show what happens with a different time step. running the same model, the same scenario. Now, when we look at the result, you see that we have essentially what looks like a red bar, but it's just so many ups and downs that it's just happening very, very quickly. It's essentially oscillating. So we get to a point here, and you can see that that's what's happening. It's going up and down, and it's very, very close, very, very close to the target of 1400. So it's 1400.1, 1399, 14.06. And so this is problematic. Our functionality of the model is fully coupled with the time step in this case. I mean, you could look at just perhaps looking at reporting steps, and then you'd say on an average, the flow is fine. But that's kind of like a proportional controller now at this point. If you're going to do it that way, which is fine actually, but I would just use a proportional controller, which does not add unscheduled steps in the first place. Okay, so anyway, I just want to make sure that's understood about the inserting of steps. Now let's go back and let's look at all the different scenarios. So I'll run all. Okay, and let's just keep going through these. So here's deadband. The next one down is proportional. And so you can see here that in this particular case, we're always slightly above the target. And we can dig into that and figure out why just by going in here and looking at the proportional controller. And you can see our bias is 0 right now. So it can help. It's not, I don't recommend it, but you could essentially try to figure out or anticipate what your inflow is going to be. And maybe it. Maybe it's simple. Maybe it's just a constant. Maybe it's an average. Maybe it's a stochastic element. So there might be ways to understand what your inflow already is. And so what I'll do is I'll go in here and, let's move this. Let's look at the inflow in this particular case. It has a mean of 10. So we're going to get a much better answer if we kind of already know that information. So I'm going to go ahead and put 10 in here, and then I'll rerun all of these models. I didn't have to do it this way. I could have just rerun this one, only this one. But okay, so now you see that it's following pretty closely up and down and around. I mean, it's still fluctuating in a similar way. It's just not hovering, above. It's centered more on the target, which is what we were looking for. Okay, and you also see, it might rise significantly above, and that is a function of our capacity in our controller. It has a cap. All right. Okay. Oh yeah, so let's go to the next one, PID. So with a PID, what you see here is that there's a big impact of the time factor now. And so there's what you could see, you could call this overreactions that are occurring. So we have this big jump right here, and that all happened starting with the problem of being too low for too long. We were so low for so long that caused a big negative reaction, which caused us to delay a response, meaning we wanted to kind of make up for this big error over here by rising above the target. So the PID controller, in essence, I would say it may not work so well for like a really large system that's got a lot of storage or a lot of capacity, but something that's more of a higher flow, lower capacity type of a system, I think would work better. PID is really good at stabilizing things. I'll show an example of that with a canal with a small time step. But okay, so there's if statement. We could compare all the scenarios, and maybe we want to just look at how the reservoir is managed, the reservoir volume. So you can see the differences here. So you might be saying, well, why would we ever want PID? I mean, look how bad that is. And yeah, so it is true when you have systems that are like this, but you don't always have systems like this. So there could be times where it is useful. The other thing I would note is that if we go up here to the PID, that it has, these three input parameters. And you'll notice here the bias is 0. So I can get away with a 0 bias here. And we're not going to be hovering over the long term because the I term is essentially doing the job of what the bias would have done. Where if we were above or below for too long, the integral term is always looking at that. So that's the comparison of those. The next thing I want to show is this model that is a canal. It's simulating a canal, and it has time steps that are 1 hour, so smaller time steps. And what it's doing is we have a changing flow, and this flow is changing on every time step. So once an hour, we're sending a different flow through here. And these volumes, they're not really small. That's actually pretty large, and I was probably doing that to make it more stable. But these kinds of systems, because water is just flowing straight through it, and there's such a short time frame between adjustments, that it just turns out that it's very difficult to keep these things to be stable. So a PID controller is more useful than the other types of controllers at maintaining stability. And so here they all are. These are all the pools with their volumes being held to a target. It turns out they're all the same target. But this is quite stable compared to what you might have if you were to use maybe just the proportional. So I don't have an example that shows that, but anyway, I'm just wanting to mention that there are types of systems where PID controller can be a bit more useful. Okay, so it's important to know, when to use each type, what they're good at. What the deadband controller is kind of like very straightforward. It's very easy to define exactly where it will operate within, and very predictable, and very simple. So there's definitely something to be said about that one. The proportional is also quite simple. It's just that you kind of have to think of it in more of a dynamic type of way. Its response is a little more complicated, and then the PID is potentially can overreact, but it can also be quite stabilizing in some situations. So one thing to consider is that you should think of those coefficients for the proportional and for the PID controller. You should think of them as tuning factors that manually need to be tuned. It's how these systems are built in the field too. It's not necessarily straightforward to calculate what they should be ahead of time. It often requires, because there's so many unknowns and uncertainties in the model, that it's not always possible to know ahead of time what the best factor should be, but you can tune it. So you run the model and you see how it responds and adjust it accordingly. I just want to mention the resources for learning how to use controllers real quick. So if you go to our website, so on our website, go to customer care, learning resources, and we have a whole section in our free online training course on how to use the controller. We also have our help system. So if you're in GoldSim, anywhere in GoldSim usually, you can either hit the help button, F1, or if you're inside of a container, maybe you're in the controller element itself, then you click help, and then it will take you directly to our help system that covers the controller element. And you can see there's a whole section in here. So I highly recommend looking into that. We also have some webinars on the controller, and we have models in our library that feature the controller application, their actual applications in which we are using a controller element. So those are the resources that you have for learning. All right, so any questions at this time? All right, so somebody asked, is the Deadband controller doing an at-stock test? That's a really good question, and the answer is yes. So back to this Deadband controller. I mentioned we insert a time step when the process variable touches the edges of the deadband, and it does that in a similar way that the at-stock test works, and that is that's an event that is triggered at the moment that a stock test occurs, and that would be at a point when the variable you're looking at is touching this boundary that's specified. So this happens. You could say, for example, specify a number, say a volume, 50 cubic meters, and then you could say, well, let me just show you in GoldSim. So you could come in here and you could have an event, a triggered event that occurs at stock test when pond is greater than or equal to 10 cubic meters. And at exactly that moment, a time step will be inserted. So that's a good question. Yeah. And the controller does that using when you use the deadband controller. Somebody asked, does placing the controller as an inflow versus outflow change where it occurs within the causality sequence? And the answer is no, it should not change necessarily unless it causes it to be influenced by other things in the model that have feedback in different ways. So there are caveats to that, but essentially the answer is that the causality is the same, which is that it does consider the initial value of the process variable, or in other words, in this case, the pond. The pond shows up here at the end, but that's its final output, which is then used as an input for the beginning of the next time step. So you kind of have to imagine state variables like a pond or a status or an integrator. You have to think of those as things that have an initial placement on this list, which is at position 0, because they have an initial state at every time step, and that's carried over from the previous time step. So the pond would be 0, and then it would inform the outflow controller, and then the outflow controller would impact the pond. And the same thing would go with the inflow controller. It'd be exactly in the same position if we switch this around. In fact, we could probably just go ahead and, I mean, it's, if we change this to inflow, right, then that means this thing right here now needs to be put into the inflow, right? We'd have to switch it like that. And then we'd have to make sure that whatever was coming in here as an inflow, which is this uncontrolled inflow right there, we'd have to make sure that that now goes over here. So the wording is unfortunate here, but that's just swapping the two. And now let's look at the causality sequence. You can see it's the same, even though it became an inflow controller. Somebody asked, can the controllers be defined as vectors? And so, no, they are only scalar. They can only be scalar. And that's similar to the pool element, which can also only be scalar. And this had to be done because of the complicated nature of emitting events that the deadband option does. It it causes an event that interrupts the clock of the whole model when a deadband bound is hit. And to have that in a vector form would be really messy, and I'm sure there are other reasons that also make it very messy in this particular case. But I think it would be quite rare to have this set up as a vector. I could see it being done, for a situation where you're modeling thousands of valves, for example. So that might be, an edge case that would be difficult to do in GoldSim to simulate that many valves. But you could definitely conceptualize, a whole valve box or a whole valve manifold, that might be controlling flows in a certain way in a general sense. But once you get down to that kind of detail, that might be where we would look at using something else. You could also use cloning, right? You could clone clone a bunch of these controllers to have them to provide a way to manage any changes to them as a group in the future, for example. Okay, well, if there aren't any other questions, then I'll go ahead and close this. Thank you for joining our June webinar, and hopefully we'll see you next month.